Hey gang, so this is the beginning of our calculus unit. So I'm going to try, and I've got a couple of videos out there. I'm going to see if I can speed this one up a little bit because the other one's a little bit lengthy. So let's take a look at differential calculus. So what is differential calculus? It's all about finding the slope of a curve at a point. All right, so I'm going to highlight that. Differential calculus. It's all about finding the slope on a curve at a point. Now you're used to finding the slope of a line, right? But what we're going to do here is I'm going to give you a curve. I'm going to give you a point on that curve, and I'm going to say, what is the slope of that curve? How you do that? You find the slope of a tangent line. A tangent line, if you remember, is a line that touches a point or touches a line at one point. So I'm going to find the slope of the tangent line, and that's going to tell me the slope of this curve. As I take that tangent line and I move it around this curve, the slope of that tangent line changes, right? Wherever I put that tangent line, the slope of that line is going to change. So the slope of that curve is going to vary as it moves around. As that tangent line moves, so is the slope of a curve. It's not like a constant line that we did before. And that's where the calculus comes in. We're going to have two different things that we're going to do with calculus. One is we're going to find the slope of that curve. The other thing that we're going to do is we're going to take 2 points on here. Remember, I've got that curve under there. And I'm going to find the area underneath that curve. I know it's kind of hard to see, but there was a line under here. It kind of went like this. Oh, there it is. I'm going to find the area under that curve. And I'm going to use something called integration to do that. And you may have heard of that before. Now, for IB math, we're going to do something called the trapezoidal rule. And what happens is if I want to find the area under this curve, you might be thinking, well, could I make a geometry? Could I make a rectangle here and then maybe make almost a semicircle up here and find the area of this and then find the area of this and add it together? Yeah, kind of, but it won't be very accurate. So we do what's called a trapezoid, and we make teeny tiny little trapezoids inside here and add them together. Anyway, it's kind of fun whenever we do it, but we do have a rule that we follow in order to do that. So we've got two main goals that we're going to try and do in our unit of calculus. The first one, we're going to try to find the tangent to the curve at any point. So the first thing we're going to try to do is we're going to try to find the tangent, and you can say the tangent line. We're going to try to find the tangent to a curve at any point. I'm going to give you a curve. I'm going to pick a point. I'm going to find the tangent line to whatever. And then after spring break, when we come back, we're going to talk about the area under this curve. We're going to find the area under the curve between any 2 points. So after spring break, we're going to find the area under the curve between any 2 points. Okay, those are going to be the two things we do it. So in order to be able to do the first one, to find the tangent of a curve at any point, if I'm going to find the tangent and I want to find this point and I want to find this tangent line, well, I'm going to have to know some information. So let's come over here. Let's draw a graph. And let's talk about this concept of a limit and the tangent problem. So what's going to happen? So I'm going to draw a curve, and on this curve, I'm going to put a point P. So if I'm going to draw a tangent line, you know what I like to use? Now, I know on your desk, or unless you're watching this at home, I wish I had my ruler. You have rulers on your desk, so if you're watching this at school, you can draw a pretty good little tangent line with that little ruler thing I have there. So here's my tangent line. If I want to know the slope of that tangent line, remind me, what do you need in order to find the slope of a line? Well, in order to know the slope of a line, you need the equation, right? You would need to say that the slope is, and typically we would say y2 minus y1 over x2 minus x1. You might say it's delta y over delta x, changing y over changing x. You might say something like that. Well, the dilemma is here that I only have 1 point. So What is the slope of P here? What is the slope of P on the curve? Well, in order to find that, I would really need another point, right? So I'm just going to put another point on here, and I'm going to call it Q. Okay, but let's look at this. If I want to know the point P, if I want to know the slope of this line right here, I would need to move Q. I'd need to move it a little closer, right? And so I might move Q down here and say, okay, let's move it down a little bit closer. But even that's not really close enough, right? I'd need to move it a little bit closer. And even then, it's still not close enough. I would need to get Q really, really close to P. Now, it can't exactly be P, because if it becomes P, then it doesn't work. So I need to think about this as if Q gets really, really close to P, but it doesn't actually become P. Here's what happens. The line PQ, and I'm going to draw it right here. I'm going to go from this P to this Q. This P to this Q. This line right here has a name. We call the line, I'm going to write it right here. We call the line P to Q. It has a name. I don't know if you know what it's called, but it is called the secant. And you might be going, oh, I remember that from geometry. I remember the secant line. When you connect point P to Q on a curve, you call it the secant line. And I would say the point P has the ordered pair x comma y, and I would say x1, y1, and I would say that the ordered pair Q would be x2, y2. And I need to make sure that they are different points. They can't be the same points. I can't say that if P was 0, 0, Q can't be 0, 0. I mean, they have to be different points in order for this to work. But I need to figure out how close can I get Q as I move it down. I need to get it really, really close, right? I need to get Q really, really close to P, really, really close to this tangent without becoming P. So you have to I'm letting you kind of soak that in. So here's what the idea is. Here's our big idea. How close can you get 2 points? How close can you get 2 points? Well, here's the answer. You can get them so close that there is literally no difference between P and Q. They're going to get so extremely close together, there's no difference. They're going to get really, 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 really close. So I'm going to put that in words, and you're like, oh my gosh, why are we writing so much? That's because these are your notes, and today we're just, there's a lot of writing. Okay, so I'm going to say you can get them so close that there is literally, I'm going to underline literally, no difference between P and Q. There's literally no difference. And then we're going to say P is, and this is so funny, when I learned how to write this way, I was like, oh my gosh, that makes so much sense when we get to the next part. P is, now here's the non-math way to write this. P is really, really, really close. P is really, really, one more, really close. Therefore, here's what happens. If P and Q are so close together, here's what happens. The slope of the secant line, the slope of P to Q, the slope of this secant line, the slope of the secant line becomes the slope of the tangent line. And that's what I'm looking for. If I can find the slope of the secant line, then it would become the slope of the tangent line. if I can get P and Q close together, the slope of the secant becomes the slope of the tangent. Now, why this really, really, really? What is this? What is that? When I talk about something being really, really, really close, this is the idea behind calculus. The idea behind calculus is that you are creating limits. When you talk about something getting really, really close, you're talking about a limit. Oh, my marker is not right. And that's what we are creating here. We are creating limits. All right. So let's just talk about a scenario. Like, how is this going to work? How is the slope of the secant and slope of the tangent going to work? So I'm going to give you an equation, a function, y equals x squared. I give you a point 1, 1. So here we go. Let's graph this. I'm only going to graph, let's just look at the positive side of this. So it would look something like this, right? And I want to know at the point 1, 1. So let's go over 1, up 1. So let's just say we're like right there. That's the ordered pair 1, comma 1. And that's the point, let's label that point P, right? Let's just call that point P. Okay. So in order, write the equation. Now, this says an equation. I am writing an equation. If I'm going to write an equation of a line, y equals mx plus b. If I'm going to write an equation, I need a point, and I also need a slope in order to write an equation, right? Well, here's what it wants. It wants the equation of the tangent to x squared at the point 1, 1. So that means, I'm going to get my little eraser here again. At the point 1, 1, there is a tangent line that goes something like this. And I need to write the equation of that line. Okay, well, can I figure out the equation of that line? I probably could. I mean, it's a pretty basic one. I might could actually just figure it out. Here's what I know. I know I have the ordered pair 1, 1. But I don't know the slope of that line. So I do need to figure it out. So it's pretty cool in calculus how this actually plays out. So I'm going to put my point Q up here. Now, I know Q technically should be a lot closer. I'm going to go ahead and just make it up high so it's easier for me to see. I know the point 1, 1. What's the ordered pair that makes up Q? So Q would be over here. I'm going to say, I would go over how much? I want it to be arbitrary. I want to remember, it's the function y equals x squared, or I could say that it's f of x equals x squared. Sometimes it's easier to think about it like that. If I go over, this is the x-axis, this is the y-axis. If I go over x, I would go up. How much would this be? I would go up, x squared. It would be whatever that function is, x f of x, if you want to look at it that way. Okay, well, this is where I get so excited because you're about to do a lot of algebra, right? Because do you know how to use your formula? All right, let's come down here. To find, let's write this, just so you have it for your notes. To find the slope, use a limit. Okay. Here we go. We're going to use the point 1, 1. And we're going to use the point x squared. All right, let's find the slope. The slope equals x squared minus 1 over x minus 1. Okay, you know how to do that. Okay, well, let's see if we can simplify this. Well, let's see. X squared over 1, or x squared minus 1. Let's factor that. X, that's the difference of perfect squares. X minus 1, x plus 1. Got to know your algebra. On the bottom, I have x minus 1. Well, I know that if I have the same thing on top and bottom, I can mark it off. That means the slope of this line is nothing more than x plus 1. Okay, well, let's see. That sort of helps me because now I know, here's what happens. As I approach x, as x approaches 1. Now, why is x approaching 1? Because here's what's happening. As you're coming down this line with your cube, let me come up here. As you're coming down from the top, and as you are approaching the value 1, as you're approaching this 1 right here, this 1, as you're approaching 1, what value are you getting close to? And then you want to know, as you're coming in from this side, as you approach 1 from the right, what value are you getting close to? Well, let's see. As x approaches 1, what happens to the slope of the secant? What happens to the slope of the secant? Now, you might be looking at that and going, well, Miss Dean, I can already see what it's approaching because I can already see what's going to happen. Well, let's see. We're going to do x, and then we're going to do what our slope is, which is x plus 2. I'm sorry, x plus 1. Okay, now remember, we can't reach 1. We're just approaching 1 because up here, remember, we're approaching 1. All right, so let's start with 4. What happens at 4? When x is 4? Let's put in 4. 4 plus 1 is 5. Okay, now let's get a little bit closer to 1. Remember, we're coming down the graph and we're approaching 1. Let's get to 3. Okay, so 3 plus 1 is 4. All right, let's go to 2. 2 plus 1 is 3. Let's go to, oh, we can't reach 1, right? So what do we need to go to? How about 2, or not 2, I'm going the wrong way. How about 1.5? So that'd be 2.5. Still can't go to 1, so let's go to 1.25. So that'd be 2.25. Okay, let's get really close. Let's go to 1.01. 1 plus 1.01 would be 2.01. Okay, how about 1.001? All right, well, that'd be 2.001. Okay, can you see what we're getting closer to? What are all these numbers getting closer and closer and closer to? Yeah, this right here is getting really close to 2. I was looking for my highlighter. So this is getting really close to 2. In fact, it actually looks like it's becoming 2, doesn't it? So that means that the slope of the secant line is getting close to 2. The slope of the secant, remember, we set it up here, the slope of the secant is the slope of the tangent. So I'm going to come up here and I'm going to say, I'm going to use my pink pen, the slope of the secant is becoming 2. Well, I know that the slope of the tangent is the same as the secant. Now here's what you're thinking. Well, could we not have just said it's x plus 1? If x is 1, could we not have just said 1 plus 1 is 2 and gotten the slope of the secant? You could have. But we needed to go through this concept because I needed you to see what's happening here before we jump to that. Okay, so here we go. We know the slope. We know the point. Let's do the math. Y minus y1 equals the slope times x minus x1. Here we go. Y minus 1 equals 2 times x minus 1. Y equals 2x minus 2 plus 1. Y equals 2x minus 1. And there is my equation. And that is the slope of the tangent line to y equals x squared at the point 1, 1. Now, that's only at the point 1, 1. That line does not work anywhere else on that line except the ordered pair 1, 1. All right, so let's take some notes over here. Let's just put a real quick little quick little note. All right. First thing I want to say is that as Q approaches P, so as we move it down, we need to remember that the slope of the secant becomes the slope of the tangent. Okay, as Q moves down, the slope of the secant and the slope of the tangent become the same thing. Now, something as moving forward that I want you to always keep in mind, why couldn't we just plug in, why couldn't we just use 1, 1? You know what, we didn't really talk about that here. Why didn't I just use 1, 1 and plugged it into this equation? And let me come over, like don't write on your paper, but let me just do that right here. Why didn't I just use 1, 1 as my point? Because here's what would have happened. If I would have used 1, 1 and 1, 1, I would have done 1 minus 1 over 1 minus 1, which is 0 over 0. 0 over 0, is that 0? Do you remember what 0 divided by 0 is? It's undefined. Division by 0, you can't do it. So, you cannot do, we can't say the slope is 1 minus 1 over 1 minus 1, which is 0 over 0. We can't do that. I'm going to put a sad face here. No bueno, because that's undefined. And we can't have an undefined slope. Therefore, x cannot equal 1. Not in this scenario. We couldn't have that. Or, what I'm really saying is that p cannot equal q. When you're going to find the slope of the tangent, p and q can't be exactly the same thing. They just have to get really, really close. You basically have to insist you must have 2 separate points. Okay, your points have to be separate. They can't be the same. Must have 2 separate points. All right, and you just did your first little bitty baby limit. Little bitty baby one. That's just a simple one. Just a little bitty baby one. Okay, now we've talked about this now. I've mentioned it a couple times. Let's talk about what is a limit. So what a function does as a variable approaches a given value, that's what a limit is. So let's come over here. Let me draw a picture. Make sure I'm on the screen there. So let's draw like a little wave, and let's put a point. We'll put a point A on here, and then let me get my pen. Okay, as I approach A from the right, and as I approach A from the left, a limit is what is happening, what value am I approaching from the right, and what value am I approaching from the left. That's what a limit is. Hopefully you're approaching the same number from the right and from the left. Okay, as long as you're approaching the same number from the right and the left, then you're good. And there's going to be a limit, it's going to be some value, and it's going to be super easy to find, and your calculator hopefully is going to help you, and it works. But sometimes there's not limits, and that's what we're going to get into here in a second. Okay, so let's just take some examples. These are super easy ones to find. Given the function f of x equals x squared, what happens is f of x approaches 2. So what we're going to do is we're going to put 2 in the middle. We're going to block off 2, because remember, we can't actually physically reach 2. We can just get really, really close. So we're going to take some numbers on the right and some numbers on the left. We can't reach 2. So let's start over here and let's do like maybe 2.5. We'll get a little bit closer. We'll do 2.1. We'll do 2.001. And then we'll go the other way. Let's do like 1.5. Let's do 1.9. And then let's do 1.999. And here's what's going to happen. As you plug these values into your calculator and you start working, what you're going to discover is that these values all get really, really close. This one over here is going to be 4.004. This one's going to be 4.41. This is going to be 6.25. Over here, you're going to have 2.25, 3.61, 3.996. And so you can see all of these values are honing in on what number as they go in? It's getting really close to 4. And so here's what you notice. They're both sides are honing in on the value 4. And you look at this and you're like, well, if I take f of x equals x squared, and I want to know as x approaches 2, what is f of 2? If I put 2 in here and square it, isn't 2 squared 4? Yeah, 2 squared is 4, and that's what I got. But you just said I can't put 2 in there. I can't just put it in there. Well, you can if it's a polynomial, and we're going to get to that down at the bottom. But for right now, just know you can't put it in here. You have to kind of work it out as a table, but in reality, you are going to be able to put it in when it works. Here's what I want you to notice. If the function approaches the same value from the left and the right for the limit to exist, the function must, approaches. The function must approach the same values from the left and the right for the limit to exist. Now, if you're a Mean Girls fan, that's one of the lines in the movie that's super, super funny. If you know that line, you'll know what I'm talking about. If you don't know the movie, you are clueless as to what I'm talking about, but that's okay. All right, so here's the way you write this. Here's the way you write a limit. If you approach the same number from the left and the right, the limit exists. Here's the way you write a limit. You write LIM, the limit, as x approaches whatever number you're trying to find. And then you put the function, which in this case is x squared. We got that the limit is 4, so we put equals, and then we put the value that you got. Okay, I'm going to box it in. This is my answer. In general, though, there is kind of a rule. In general, here's the way you might see it written in your IB exam. It might be written like this. The limit as x approaches, and I'm going to say a because a is going to stand for some constant that it's approaching. F of x is going to represent our function, and it's going to be L. In general, if we approach a of some function, it's going to equal L, and the rule is going to be that x cannot equal a. That's going to be our restrictions. Now, x never reaches a. That is our big guideline here, is that x never, and that's what I was saying here. Remember, we never ever reach a. We get really, really close to it, but we never physically reach it. That's why we block it out on here. X never reaches a. It just gets, and here's that really, really, x never reaches a. It gets really, and if you want to put 2 more reallys, you can, close. Okay, that is super important. It never reaches it. It just gets really close. Now I have another example on here that I will put, and this is the limit as x approaches 1 of x minus 1 over x squared minus 1. I put this one because this one you were like, oh my gosh, you could just plug it in and you get 4. What happens here when you plug in 1? 1 minus 1 over 1 squared minus 1. Oh, you get 0 over 0, which is undefined, and bam, you suddenly cannot work this one, right? So this one, you physically have to work it out. So remember, we're going to say as x approaches 1. So we're going to put 1 in the middle, and we are going to block it out because we can't actually reach 1. So just so that we all have the same numbers, we're going to put these in. I'm going to put in 1.5, and then I'm going to put in 1.01. I'm going to put in 1 point, and then 3 zeros. 1, 2, 3, 1. And then I'm going to put in 0.999. I'm going to put in 0.99. And then I'm going to put in 0.5. Okay, and I'm not going to use that last one. All right, starting on the far left, I'm going to get 0.6666. And then I'm going to get 0.5025. I'm going to get 0.5002. Skip that next one, and then we're going to get 0.4999. then we're going to get 0.4975, and then we're going to get 0.4. So, coming in from the left, we are converging on 0.5, and coming in on the right, we are also converging in on 0.5. So, I can see that the limit, what are we approaching from both sides, is 0.5. So the limit as x approaches 1 of x minus 1 over x squared minus 1 is 0.5. All right. Now, sometimes when you have a limit, what if the limit does not exist? So you have to look at these limits hand in hand, and just take it piece by piece and see which way it's going to go. So graphing it is by far one of the best ways to look at these. So let's take this situation here. This is called a left-sided limit. This is a right-sided limit. Here's how you write a left-sided. You say the limit as x, and what number are we approaching? We are approaching the value of 2. We're approaching the x value, because remember this is x approaching what value? Not y, but x. As x is approaching the value of 2. Now, we want to say it's from the left side. To show it's from the left, we put a little negative up there. It's not a negative 2. It's just saying from the left side. Notice it's on the wrong side to be saying negative 2. If I was going to say a negative 2, wouldn't I put it on this side like this, negative 2? And that does not say negative 2. It's on the wrong side. Now, I want to say of f of x, of whatever this function is here. The limit as x approaches negative 2, what does it equal? Well, it equals the y value. What is the y value? From the left side, as I come in from the left, here's the graph on the left side. The right side's over here. So as I come in from the left, I'm approaching negative 1. So I want to say it approaches negative 1. Okay. So let me highlight that. And I'm also going to say from the left, I approach negative 1. Okay, now I'm going to write the next one. I need to find my highlighter. There it is. And I'm going to do the same thing. And I'm going to say the limit as x approaches 2. I'm still approaching 2, but this time I'm coming from the right. So I'm going to put a little plus sign of f of x. And I need to look and say, okay, as I come in from the right-hand side, what value am I getting close to? Well, on the right-hand side, I'm getting close to 1. So I would say this is 1. Well, here's the thing. Coming from the left, I'm getting negative 1, and coming from the right, I'm getting a positive 1. So now I need to draw a conclusion. So the limit as x approaches 2 of this whole scenario here of f of x, well, let's go back and read that statement. The function must approach the same value from the left and the right for the limit to exist. Yeah, the limit does not exist. So here's what we say, does not exist. I wished I had another color, and I don't think I do. I do have a red marker, an orange marker. I didn't know what color this was. I'm going to put it in orange right there. So the limit does not exist. Okay, so I've got 2 examples down here for you to try. Here we go. Example 4 and 5. So we're going to write this, the limit. We're going to write it, I think I write it, yeah, I write it all 3 ways. So we're going to write the limit as x approaches, and we are approaching, from the left, we're approaching 2, from the left of f of x. And then we're going to do the limit as x approaches 2 from the right of f of x. And then we're going to do the limit of f of x as x approaches 2. And we're going to do the same thing on this one over here. All right. As we approach from the left, so I'm going to do this one in pink. Coming from the left, we are approaching, remember, we're approaching the y value. That is 1. So I'm going to highlight that one pink. And then as we approach from the right, the y value is 3. And so, ooh, these are not the same. So that means my function does not exist. Okay, well now let's try the other one. So this one's going to be the limit as x approaches, looks like 5 from the left of f of x. And then I've got the limit as x approaches 5 from the right of f of x. And then I've got the limit as x approaches 5. Okay, well, here we go. As we approach from the left, I am approaching, looks like 3 from the left. And then, I forgot to highlight this over here. As I approach from the right, I'm still getting really, really close to 3. I know I've got that up there, but I'm not getting close to it. I'm getting close to this hole right here, which is at 3. So that's also at 3. Okay, well, are those the same? Yeah, so that means the limit as I get close to 5 is 3. Did I even pay attention to that right there? I didn't, because I don't ever get to it. I'm just getting really, really close to 3 right here. If I ever actually reach 3, I'd jump up to 5, but that hole right there doesn't even matter. I don't even get close to it. All right, so I'm going to highlight this pink. I'm going to highlight this one yellow. And so my limit was 3. So as long as you're approaching the same value, your limit does exist. All right, so let's put in our statement up there. If the left and the right side limit do not approach the same value, then the limit does not exist. So put that in there. If the left and the right side limit do not approach the same value, then the limit does not exist. Okay, find the limit of f of x equals 1 over x as x approaches 0. All right, so we're going to do the same thing. So we're approaching 0. When I put 0 in here, 1 over 0 is undefined. So I already know that something's up with this one. So I'm going to put my 0 in here. And, oh, I put it in the wrong spot. 0 in here. And then I'm going to block off this bottom one, because remember, we're not going to actually reach that. And then let's do 0.001, 0.01, 0.5, and then we're not going to use that last one there. And then let's use negative 0.5, negative 0.01, negative 0.001. All right, and I'm going to go ahead and go down here on the graph. While you put those in, we're going to do, let's see, I'm going to give you these numbers. This is negative 2, this is negative 100, this is negative 1,000, this is positive 1,000, this is positive 100, and this is positive 2. Now, here's what I noticed. I noticed on this one that I kind of needed to go to my graph and graph it. So I'm going to do 1 over x, and I'm going to graph it so that I can kind of see it. And so I'm kind of like, oh, I kind of remember this one. It goes up here. Kind of looks like that. It had some asymptotes in it, right? So it kind of looks like that. So I'm like, okay, well, let me go over here. The limit as x approaches 0 from the right. And I'm just going to put f of x for this. And then I'm going to put the limit as x approaches 0 from the left. And I'm going to have to figure out, because this one's got, it's not going to the same number, right? This is 1,000 and this is negative 1,000. So it's not doing the same thing. So I'm already thinking, is this the limit does not exist? Because like, it is not doing the same thing. So I'm thinking it doesn't exist. So something's going on because I've got an undefined situation. What I notice is as I come in from the right, this is going up to positive infinity. And I notice that this, as it gets closer to 0, that as it goes this way, this is going to positive infinity. And I notice as it comes in from this way, that this way is going to negative infinity. So this way is going down really fast, and this way is going up. So as I come in from the right, it's going up over here to positive infinity. And as I come in from the left over here, it's going down to negative infinity. Are those the same direction? Like, no, not at all. Those are completely opposites. And so what you're thinking is actually right. You're thinking, well, the limit doesn't exist because it's not going the same direction. And you would be right. The limit does not exist in this scenario. Just like with numbers, if it's going to infinity, if it's not the same infinity, if it was both going up to positive infinity, then the limit would exist. The limit would be positive infinity. If the limit was both going down to negative, then the limit would exist. It would be negative infinity. But if the limit as it goes to infinity, if it gives you that vertical asymptote, then we're going to have it doesn't exist because it has to be the same. So if the limit as x approaches a is positive or negative infinity, it gives you a vertical asymptote. Anytime you get infinity, you're going to have a vertical asymptote. So let's just put it there. So if the limit as x approaches a of f of x equals positive or negative infinity, then you have a vertical asymptote. I'm going to try and all right, and so what I'm going to do down here is I'm just going to give you real quick, I know everything in this lesson is so quick, we're already at 42 minutes. I'm going to give you some scenarios where we come in on this, okay? So one scenario is, let's come in from the right, so let's come in from the right this way, and then let's come in from the right this way. So we could come in from the right, and we could shoot up to positive infinity. But we could also come in from the right and we could shoot down to negative infinity. So we could go up to positive infinity or we could go down to negative infinity. Now let's come in from the left. So let's come in from the left. Come in from the left, we could do the same thing. We could shoot up to positive infinity, right? But we could also, coming from the left, shoot down to negative infinity. Okay? Those are the only possibilities that you could get. Now, let's write the limits and what that would look like in each of these scenarios. It's pretty easy to say, oh, I understand the graphs. That's algebra 1. This is coming from the right, I'm going to positive infinity. Coming from the right, I'm going to negative. Coming from the right, coming from the left, I'm going to positive. Coming from the left, I'm going to negative. Let's write the limit. This would be the limit as x approaches a, and we want to say we're coming from the right, so we're going to put a positive. And we're going to say from f of x. This would be, we're going to positive infinity, so we're going to say it goes to positive infinity. How would we write this? This would be the limit as x approaches a, again from the right, of f of x. And we would say it would equal, though, this time we're shooting down to negative infinity, so we would say it equals negative infinity. On the bottom ones, we would say it's the limit as x approaches a from the right of f of x equals, and it's shooting up, so we would say positive infinity. On the last one, we would say it's the limit as x approaches a from the left. Oh, I did that wrong, didn't I? I said from the right. Pardon me, that would be from the left. That one's from the right. That one's from the right. This one's from the left. And this one's from the left of f of x would be negative infinity. From the right, from the left, from the right, from the left. There we go. So that was just notation. I just wanted you to see that notation again so you could see how it's written. All right. So let's take a quick second and let's look at limits and what they look like whenever you are working with them. These are the properties of limits. So there are three basic properties now that you kind of see what they look like. 1, 2, and 3. All right, the first one is the limit of a constant. If we take the limit as x approaches a of a constant c, whatever that constant is, it doesn't matter what it is, when you take the limit as x approaches a of a number, the answer is just that number. What would that look like? That would be as x approaches this number a, here's your constant c. C would be like your y-intercept. It would be a horizontal line. It would look like that right there. That's what the limit would be. Okay. The next one property is the limit as x approaches a of the variable x. If you just have a single variable and you take the limit of it, whatever number value a is, that's going to be what the limit is. Okay, what would that look like? That would be, if you're coming out here a, whatever the a is that you're approaching, that's what it's going to look like here. It would look very linear. If you go out a, you would go up a. If x is 1, you would go up 1. If x is 2, you would go up 2. If x is 3, you'd go up 3. That's what that would look like. And the third one is the one we just did a second ago. See if I'm going to kind of go up here to write this because it's kind of a big one. I'm going to say the limit as x approaches 0 of 1 over x. What we just did, we said it goes to negative infinity if it approaches from the left. And then we said the limit as x approaches 0 from the right of 1 over x. We said that went to positive infinity. And now on this one, remember we had our graph going this way, and we had our graph going this way. So just a reminder, when we came in from the left, we went to negative infinity. When we came in from the left, we went to negative. And when we came in from the right, we went to positive infinity. Came in from the right, we went to positive. Okay? That's just a reminder. We just did that one like just 2 seconds ago. Okay. You want to commit these. I know you're not going to like to hear this, but you kind of want to memorize these. You will the more we work with them, but these are kind of what you want to memorize. Now, what I'm going to do, and you honestly you will, by the end of this lesson, you'll probably have all 3 of these memorized. I want to take this, and I want to show you how to work with these limit properties. So I want to take the limit as x approaches a of f of x equals L1. This is like my first rule. And then I want to take my second one, which is the limit of g of x as x approaches a, and say that it equals L2. And now L1 and L2 are just representing the answer. They're not really representing anything of value just yet. And so what I want to do is show you these properties. Think about these as like properties of equations, only they're with limits. So what if I took these 2 limits and applied the property of addition? Here's what I mean. What if I took the limit as x approaches a, and I said of f of x plus g of x. Okay, what I want to do is say, if I have this scenario where I'm adding these, I can break them apart and say, that is the same thing as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. In other words, I can break them apart and make it into 2 separate limits. It goes without saying that if I'm adding, I could also do subtraction. It works for both of them. Okay, number 2. What if I'm multiplying? Well, if I have the limit as x approaches a of f of x times g of x, guess what? You can break it apart and you can say the limit as x approaches a of f of x times the limit as x approaches a of g of x. It works the same. All right, the third one is division. The limit as x approaches a of f of x over g of x. Now you might be thinking, well, we can't have a denominator issue, and you're right, we're going to have some boundaries. What I'm going to say is that I'm going to take the limit as x approaches a of f of x over the limit as x approaches a of g of x. And the limitations are going to be that g of x cannot be 0. All right, number 4. This one we won't use a whole lot, but if I have the limit as x approaches a of f of x, and I have it raised to the nth power, this property says it's okay to take the limit first of f of x, and after you do that, then take the whole thing and raise it to that power, whatever that power is. And then the last one, it kind of goes along the same thing. It is if you have a radical. Okay, so if I have the nth root of a function, it just says that I can do the exact same thing. I can take the limit as x approaches a of f of x, and then after I do that, then I can take the nth root of that at the end. All right, so I'm going to do this next one. I am going to take the long way around to do this, and then afterwards, I'm going to show you the shortcut. So here's what I've got. The limit as x approaches 2 of x cubed minus 2x plus 7. I'm going to take this polynomial, and I'm going to apply every one of these to it in order to solve it. All right? So here's what we're going to do. We've got subtraction and addition, we've got cubes, and we've got multiplying. I know that if I have subtraction, multiplication, all this other stuff, here's what I'm going to do. I'm going to say the limit as x approaches 2 of x to the third minus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 7. I can break it apart so that it's easier to work with. I know that the limit of a constant is just that constant, right? I know that the limit of x cubed, I can take the limit of x and then cube it. So this will look like this. The limit as x approaches 2 of x, and after I figure that out, then I can cube it. Minus 2 times x, well, that's the limit as x approaches 2 of 2 times the limit as x approaches 2 of x. Now I'm going to put this like this. There's that constant again. I know that the limit of a constant is just that constant. Okay, I'm going to go ahead and do this. The limit as x approaches 2 of 7, go back to your rules, the limit of a constant is just the constant. So that means the limit of 7 is just 7, right? So I'm going to go ahead and say, well, this is just 7. The limit of x is just the value of whatever a is. So if I'm approaching 2, that means this would be 2. So that means this would be 2 to the third power. Minus, if I'm approaching 2, then that means this one right here would just be 2 times x. So that means I'm approaching 2. So I'm going to do 2 plus 7. 2 to the third is 8 minus 4. So that's 4 plus 7 is 11. So there's my answer. Now, here's what some of you may have already done. You may have said, oh my gosh, Mrs. Dean, what if you go back up here and can you just plug that in? Seriously, Mrs. Dean, what if you said 2 to the third power minus 2 times 2 plus 7? Isn't that 11? Why'd you do all this? Well, I needed to show you this because this is how you break it apart. Because what if I asked you to show me the properties? Show me how to solve this limit using the limit properties. Could you do it? Yeah, you need to know how to do that because IB exam, we could ask you how to do that. But to find the limit of a polynomial, which is what we just did, oh yeah, you just plug it in. Isn't that nice? I know. The polynomials, they're really nice. You just have to plug it in. You just plug it in and you check it. So here's what I'm going to say. I'm going to say the limit as x approaches a of polynomial in the function x is you just evaluate it for a. And so I'm going to write this. Maybe this will help you. Polynomial p. And I'm going to say evaluated at a. That way you'll know what it says there. All right. We are rocking and rolling. Okay. So now that we know how to do that, let's go here and let's see if we can do this. Okay. So the limit is 4x squared plus 1 over x minus 3 as x approaches 2. So, well, let's see. That would be 4 times 2 squared plus 1 over 2 minus 3. Well, pretty sure that's, let's see, 2 squared is 16 plus 1 is 17 over 1. That's negative 17. There you go. Now, one thing I want to point out to you, if you wanted to rewrite this and say, the limit as x approaches 2 of 4x squared plus 1 over the limit as x approaches 2 of x minus 3 equals negative 17, that is the better way to write that one because you're showing that it's the two limits over everything. You always want to be sure that you check the denominator for domain issues. This one did not have domain issues because if it had it as x approaches 3, we'd have had issues and then we'd have to figure something out. But this one did not have domain issues. This next one, however, it does have domain issues. Okay? The next one does have domain issues because zeros in the denominator are not good. Denominator, domain issues. Let's put this here. Let's put, be careful of zeros in the denominator. And let's highlight that. We want to be careful of that. So, in this next one, we definitely have some issues. So here's what we can do. Let's see if we can do some algebra and factor out the issues. So here's what I'm going to say. I'm going to say the limit as x approaches 2, but I'm going to take x squared minus 4 and say, you know what? That's the difference of perfect squares. That's x minus 2 times x plus 2 over x minus 2. Let's see. That's the limit as x approaches 2. Well, let's see what happens. X minus 2 and x minus 2 cancel out, and that's just x plus 2. Can I solve that? Yeah. Plug in the 2. 2 plus 2 is 4. So the limit as x approaches 2 of x plus 2 is 4. Let's put here denominator issues, sad face, boo. So we had to fix it. All right, so real important to know is that wholes factor out. If you have wholes, they will factor out. But if you have asymptotes, they won't. Remember, the asymptotes are where we're going to go to positive or negative infinity. Something's going to happen there. A lot of times the limit won't exist when that happens. So this particular one, x plus 2 and x minus 5, as we approach 5, we can't factor anything out, right? So we're going to have to do what's called a sign analysis test. That just means we're going to check and see what's going on here. A lot of times you can simply go right here and say alpha y equals, and just check what the graph looks like, x plus 2 over x minus 5. Can I just graph it and see what it looks like? Okay. I know that there's something going on here at 5, right? I can see that there's domain issues. So I can see over here at 5, I'm going to actually even do this because I can see clearly at 5, my graph does something like this, and then it does something like this. My graph's got some issues going on. That's what it looks like. Okay. So it's like, what is going on? So I'm going to put a note over here, and I'm going to say this has some domain issues. I can't factor it out. It's not a whole. We definitely have an asymptote. So I want to look at, I'm going to say, look at the graph. Okay, I'm going to look at the graph. I'm going to be like, what's going on with my graph? Oh. Okay. I think oh no, it's still going. I thought my computer just stopped. So I'm going to look at the graph. I definitely graphed it in the calculator, and I sketched the graph. And so I noticed that up here it's going to positive infinity, but I know here it's going to negative infinity. So what does that mean? That means the limit as it approaches 5, it does not exist because it's not going to the same thing. So you have to do what's called the sign analysis test, positive and negative infinity. You want to check it out. So the first thing you're going to do is you notice that you get that 0 over 0. You get that scenario where you get an undefined scenario over here where something doesn't work. So you try to factor out the whole. Try to factor out the whole. And in this situation, we couldn't. Okay, so we tried to factor out the whole and simplify, and it did not work. If you can't factor and simplify it, then you have to do the sign analysis test. And check positive, negative infinity. I'm going to say and graph it. And that way you can see what's going on. Graphing is actually the best way to see what's going on, to see if you can see what is going on with that limit. All right, so you are now officially done with this first part. It took about an hour or so to get through that. Hopefully my video kept working. It looks like it's working. I'm not sure. And you are to the check for understanding. Thanks for watching.